In this lesson, we're going to wrap up our discussion of transformations of exponential functions. And in this case, we're actually going to reverse that process. So up until now, we have focused on the idea of from an equation, can you produce the graph or a sketch of the graph? Now we're going to say, what if you are given some final information, whether it's a description, whether it's a list of points, or most typically, whether it's a graph, and you are asked to find the equation for that graph. This is actually a very useful application of these transformations because one of the things that you may wish to do with exponential functions is to model some data that you have that looks exponential, and then you want to come up with an exponential equation that you can then manipulate related to that data, use it to extrapolate, make predictions, calculations, etc. In order to do this, you can make your life much easier by always ignoring, and I say that here, what you want to do is ignore, if I can get my highlighter, you want to ignore all horizontal transformations. So what we're going to do is make use of the idea of an equivalent form. So I've got some examples here. For example, here I have what a horizontal reflection looks like. Y equals 2 to the negative x. I have a negative in the exponent. But we can actually come up with the exact same graph, which means an equivalent form, if we write that with a different base instead. So a negative exponent can be written with a positive exponent if we change the base, because we know that a negative exponent means that I can take 1 over the base instead. If we have a horizontal shift, for example, I'm adding or subtracting some constant in the exponent, I can use my exponent laws to write that as, and I'm just going to make that really clear here, that's the same as 2 to the 1 times 2 to the x. We know that 2 to the 1 times 2 to the x is indeed 2 to the x plus 1. So again, I've removed the horizontal transformation here by thinking of it instead in this equivalent form. But this equivalent form, by moving that value to the front, it's now a multiplying factor. It's actually the a value. So this would be a vertical stretch. And then in this case, what happens if I have in the original expression, I have a k value? It is possible to once again use my exponent laws to rewrite that. So instead of 2 to the 3x, where I group the 3 times x as kx, I actually use a power of a power. So I group 2 to the 3 all to the x. We know if we were simplifying this, 2 to the 3 to the x, we would take 3 times x. That would take us back to the original. But in this case, by changing the base from a 2 to the 3, we can simplify that to be 8 to the x. So that means that we never really need to consider horizontal transformations. Now, if that's convenient for you, that's perfectly fine. That's a good reason to use horizontal transformations. But in general, they are going to complicate things, and if we can avoid them, it's generally going to be for the best. So if we take out all consideration of horizontal transformations, we end up with only having to deal with essentially 3 parameters. The first is the base of the exponential function. The second is the a value. I didn't need to write the letter a. I meant to write the number 2. And the third is the vertical shift, or the q value. And then the order in which we deal with these things actually gets jumbled up a little bit as well. And that's just based on the simplicity of which one to deal with first. If, for example, you are looking at a graph, the most important feature on an exponential graph is the horizontal asymptote. And the only thing that affects the horizontal asymptote is the q value, is the vertical shift. So if you can see the vertical asymptote, then you know what your q value is right away. The b value, the common ratio, is probably the most complicated thing to discover Now, there are going to be a lot of situations where the B value is completely easy and straightforward to discover, so I don't want to make it sound worse than it is. In the situation where you can see the horizontal asymptote, if the horizontal asymptote has not moved, in other words, if your Q value is 0, then you just take the ratios of the successive y coordinates. And that is fairly simple, fairly straightforward. Then, if there is a vertical shift, we are going to use ratios, but we can't use the ratios of the raw y values. Instead, we have to use distances from the horizontal asymptote. Otherwise, it looks exactly the same. I'm going to illustrate these with examples, and you're going to see me do this A situation and then this B situation. And then if you cannot see the if you cannot see the horizontal asymptote, you may actually be forced to take the ratio of the first differences, which is more work still. And I'm going to end up, I added it just for this video, I'm going to finish with a fairly complicated example, at least complicated for this type of question, where I have to do this 2C option. That will happen very rarely, if ever, but it is something to keep in mind if you're ever dealing with less cooperative data. Okay, so also a little bit of a side note here, a little bit of a warning. The B calculations assume that all of the points you're using have a delta x equal to 1, meaning that they are one step to the right or one step to the left as you work through them. If you don't have a delta x equal to 1, this is the one situation where you get forced to introduce one of the horizontal scaling values, which is the k value. I'm going to illustrate that again with the last example, and then I'll show you how we can then simplify our equation to go back to having only the A, the B, and the Q. Now, if you happen to be able to see the y-intercept on your graph, you can also make use of that y-intercept. Now, the easiest way to make use of that y-intercept is just to do a substitution. But there's actually a little trick that you can also make use of. This is based on the mapping rule, if you're familiar with that, which is that the original y-intercept, which is always at 0, 1 for an exponential function, has been moved to a plus q. The q has moved the asymptote, and then the a describes the distance from the asymptote. And so overall, you get this a plus q combination. I'll try to illustrate this for you, but really I generally prefer for you to do something a little bit more honest, which is just to sub the point in. And note that we are here assuming p equals 0. We are, once again, we're not working with any horizontal shifts. We're going to assume that it has not shifted to the left or right. And then we get back into the more difficult scenario, which I partially described already. If some of these easier features are not available to work with, the asymptote being the best one, that's the thing you most want to see. And the y-intercept can actually make your life quite a bit easier as well. If you can't do that, then you can substitute known points and you can solve for unknown values, essentially creating a system of equations. And once again, my most difficult example, or my most complex example, is the last example. I'm going to illustrate number 4 here that way as well. But before we dive into complex examples, let's look at about the easiest example that you could start with when you're doing something like this. And here I have a description. I want the equation of an exponential function. It has a common ratio of 3. So we're basically just reading information from this description. It has a y-intercept at 5, which means that there is a point at an x-coordinate of 0 and a y-coordinate of 5. And it has a horizontal asymptote at y equals -2. Now, I normally start with the horizontal asymptote just because it is so obvious, it is so direct. That tells us that this has been shifted down by 2. And of course, it's telling us the b value, so the b value is 3. So from there, I can go to my equation. Normally, I'm going to write it in the form ab to the x plus q. So in this case, I'm going to end up with a, but instead of b to the x, I now know my b value is 3 to the x. And instead of plus q, I know that it's minus 2. The fact that we know this point at 0, 5, so this is right now my description of the function. You could write this as y equals as well. Now I'm going to sub my point 0, 5 in here. So the y value becomes 5. The a is the unknown we're going to solve for. 3 to the 0 minus 2. And this highlights for you why is knowing the y-intercept so useful, because we know that anything to the 0 is just equal to 1. And so this becomes, I add 2 to both sides, and I end up with a equals 7. So therefore, this exponential function that was described here is 7 times 3 to the x minus 2. Now, I mentioned on a previous page, I said that we can assume the y-intercept has moved from 0, 1 to 0, a plus q. So I'm only going to make use of that this one time because it's not my preferred approach, but it is. There's no denying that it can be convenient if you remember it. So if we use the mapping rule, which tells us that 0, 1 has moved essentially to 0, a plus q, then that means in this case, a plus q, we know that the y-intercept was at 5. So that immediately tells us that a plus q must be equal to 5. But we know what q is. Q is negative 2. So a minus 2 is equal to 5. And a is equal to 7, which of course we know is the correct answer. We already came up with that. Let's move on to some graphs. So here we have a graph that represents what I consider to be the simplest situation for a graph. We are, first of all, and I'm going to do this in order of the features, so I'm going to start with the asymptote whenever I can. So we can see here we have the horizontal asymptote. It used to be y equals 0, and so that's on the dotted line, that's the parent function. And then we have moved to y equals 0, which of course that tells us that our q value is 0. So we already have one of the values that we need. Our b value, since our q value is 0, then to find my b value, I'm going to do the ratio of y values, or of y coordinates. And so my first y coordinate here is at 2. So I'm going to say that y1 is at 2, y2 is at 6, and y3 is at 18. Notice that for these y values, the x values are increasing by 1 at a time. So in each case, I'm taking a step over by 1, and then I'm taking a step over by 1. That's important for us to use this simpler method. It is also important that we read these y values from left to right. So overall, when I read my y values, it's important, no matter what the shape of the graph is, that you read from left to right. And there's a lot of times where we specify that when we talk about from left to right. So in this case, we're reading from left to right. Now I go ahead and take my ratios. So I'm going to say, okay, how about y2 over y1? y2 over y1 is 6 over 2, and that's equal to 3. Technically, that is enough. But if you have the points available, it is always a good idea to take another ratio. So in this case, I have y3 over y2. That is 18 over 6, which is equal to 3. And since these two values are the same, so they are the same, and that's a good thing, so that tells us that our b value is equal to 3. From there, I can write my function, g of x is equal to, it was going to be a b to the x plus q, but now I can write that g of x is equal to a 3 to the x, and q was 0, so it's just a times 3 to the x. And so let's now sub our one known point. Our y-intercept is at 0, 2. And so the y-coordinate is 2, a times 3, but this is 0, and so you get an immediate result, which is that a is equal to 2. And g of x is equal to 2 times 3 to the x. If you wanted to confirm this, you could now substitute these x coordinates, 0, 1, and 2, and make sure that you got the corresponding y coordinates. For example, when I put in x equals 2, 3 to the 2 is 9, times 2 is 18, and that is the y coordinate that goes along with it. Okay, ramping up the complexity, not terribly complex yet, but definitely more so because we have our asymptote has shifted. Now, my scale might not make this completely clear to you, so I'm actually just going to make sure that you're not wondering about this. This new asymptote occurs at y equal 4. And so from that y equal 4, I mean, it's just that easy. That tells us that our q value must be 4. So that's always where I start. First step, if I can, I'm going to identify the q value. Now in this case, for my b value, I'm not going to be able to take the ratio of y coordinates because the asymptote is not 0. So now I'm going to take the ratio of distances. And those are the distances from the horizontal asymptote. And it's really not that much more difficult than what we were doing before. The only difference is now instead of just reading these y coordinates straight off of there, I have to come up with distances from the asymptote to that y coordinate. If the asymptote is at 4, this y coordinate is at 7, that's a distance of 3. If the y coordinate is at 4, if the asymptote's at 4 and this y coordinate's at 10, that's a distance of 6. And if the asymptote is at 4 and the y coordinate is 16, that's a distance of 12. So remember, just like we did before, we're going to read these from left to right. So that means what I'm going to label as distance 1 is going to be that 3. Distance 2 is going to be that 6. Distance 3 is going to be that 12. So what is the second distance over the first distance? That's 6 over 3, and that's equal to 2. What is the third distance over the second distance? That's 12 over 6, which is equal to 2. And that's good news. Those two ratios are the same, so that means our b value is equal to 2. And that's our second step. And now we go on to, I'm going to write my equation. And since I've just been changing the letter, h of x, a b to the x plus q. I don't know a yet, but I do know the base is 2 to the x, and I know the q value is 4, so that's h of x. And it turns out, now I could do this, I could sub any point. I just want to make that clear. I could sub any known point to find out what my a value is. I have the y-intercept, so why not use that? But you know what? To illustrate it, why don't we go ahead and I'm going to choose a non-trivial point. So let's choose 2, 16. Okay, so I would prefer, what do I want to say here? The y-intercept is just easier, okay? It's not better for any reason other than the fact that it has an x-coordinate of 0, and that just x-coordinates of 0, 2 to anything, or sorry, anything to the 0 gives us 1, and that's very convenient. But just to show you that it doesn't matter, the y-coordinate is 16, a 2 to the power, and this is going to be 2 to the power 2, plus 4. So 16 minus 4 is 12, and 2 to the power 2 is 4, so this is 4a, and so I end up with my a value of 3. So it's not as if it's that, especially not for simple values like this. So now my function h of x, I've got my a value is 3, 2 to the x, plus 4. Sorry, that just jumped to a different page. I think that's where we ended off there. H of x, yes. Okay, let's take a look at another example. And again, I don't think it's illustrated particularly well, so I'm going to just fill in for you here that this is y equals -3. So the asymptote is at y equals -3, and that immediately tells us our q value. Q equals -3. And then from there, I can take my, actually, you know what, in this case, rather than guessing at that y value equal -3, why don't we operate as if it's unknown? Let's say that the scale is not good enough, and so I cannot reliably make a statement about where it is. Yes, it looks like it's at -3, but let's say that the scale is even worse. If you don't know, first of all, the q value is not 0, so we can't just do the ratio of y values. The q value is actually unknown here. And since I don't know the q value, I don't know where this asymptote is. I can't do the ratio of distances. So now for our b value, we get forced into this new scenario, which is we have to do the ratio of first differences. And the first differences, just to remind you, those are the change in y values. So in this case, now I do need to do this again from left to right. I just want to keep reinforcing that idea. So I'm going to read from left to right. That means that my first y value is going to be 17. My second y value is going to be 7. My third y value is going to be 2. And so these two, that's going to be my first difference, which is going to be 7 minus 17, which is -10. And then my second delta y2, is going to be 2 minus 7, which is -5. Now the downside to this is you can see that whenever we use the first differences, we lose one piece of data. That means that for my ratio, I'm only going to be able to do a single ratio, which is, again, from left to right, it's going to be delta y2 over delta y1, and that works out to be -5 over -10, which works out to be +1/2. And so since we have no other ratio to compare it to, but our graph looks pretty good, we're just going to have to rely on that. We're going to assume that that single ratio is enough. So let's see, I'm just going to say y equals this time. And so a b to the x plus q. And what information do we have? Now we don't have the q this time. That means it's a 1/2 to the x plus q. This might be a situation where you decide you want to make use of that mapping rule. The mapping rule tells us that the y-intercept went from 0, 1 to 0, a plus q. So that might be pretty convenient. If you sub in the value, it gives you the same result here. So that tells us that a plus q must be equal to 2. Actually, you know what? Even that on its own, that's not going to tell us enough. So even though we could use the mapping rule there, I think it is better for the sake of consistency. Because we have two unknowns, we need two equations. And I'm not going to use the mapping rule just because I want to do this kind of very formally, which is that means I'm going to sub 2 points. If I sub 2 known points, that will give me my two equations and I can manipulate those. So I'm going to use the two simplest points I have, -1, 7 and 0, 2. So that gives me a y value of 7, a 1/2 to the -1 plus q, that's my first equation. And then a y value of 2 equals a 1/2 to the 0 plus q. That's my second equation. Let's do a little bit of simplifying. 7 equals 1/2 to the -1 is just the same as 2. So this becomes 2a plus q. And then 2 equals, well, 1/2 to the 0 is 1. That's why it's such a nice x coordinate to use. So we get a plus q. So equation 1 and equation 2. And now we use our skills from linear equations from grade 10. And we're just going to do solving of this particular system. It's a pretty simple system. I'm going to take equation 2 and I'm just going to rewrite it underneath equation 1. And hopefully you can see that if I take equation 2 minus equation 1, 7 minus 2 is 5. 2a minus a is just a. And q minus q is 0. That tells me my a value is 5. So now my equation is, well, actually, you know what? Now that I know my a value is 5, how about I just substitute that 5 right here, and I end up with 2 equals 5 plus q, and we end up with a q value of -3. And I was going to give that to you, the y value. I was going to say that it's at -3, but you can see that we can obtain that through algebra if we have to. So our final equation here is 5 with a base of 1/2 to the x minus 3. And now I'm going to finish off this video. This is something that I added in the last minute. I just want to put it all together here. In this case, I've really made the worst combination for the scenario. The horizontal asymptote is not given, and it's not clear from the graph. The y-intercept is not given, so we can't even use any kind of shortcuts. We're not going to be dealing with any convenient values. And I've also got the situation here, if you notice, my x-coordinates are not, they are consecutive, but they are not consecutive by steps of 1. They're actually steps of 1/2. So we're going to have to incorporate that into our equation as well. I'm going to start with that just because you might have forgotten I did talk about it. So our equation, normally the equation in general is going to be a b to the x plus q. But there's an additional piece that we have to consider, which is the step size, which I call delta x. In all of our previous examples, delta x has been 1. All the x values have been increasing by 1. So this has been x over 1, and that's been fine. But in this case, our delta x is not 1. So we are actually going to write this as a b to the, and then we're going to write this as x over, and our step size is 0.5 plus q. And that simplifies to y equals a b to the 2x plus q. So that's going to be the equation that we're working from here. This is a situation where we get forced into using one of the horizontal transformations, at least for now. In the absence of this asymptote, to find my b value, I'm going to have to do the ratios of the first differences. Reading from left to right, the first y coordinate that I encounter is 8. The second y coordinate is -4. The third y coordinate is -28. Those first two gives me a delta y. The first delta is -4 minus 8, which is -12. The second first difference, the second delta, is -28 minus -4, which is -24. Again, I only have a pair of these to use. So my 3 points has turned into 2 deltas. So my ratio is just going to be the b value. I don't get to compare it against anything else. It's going to be delta y2 over delta y1, which is -24 over -12, which actually works out to be a fairly simple b value of 2. So now my equation is y equals a 2 to the, and don't forget it's 2 to the 2x now, plus q. And now I'm going to sub a couple of known points just to work with. Actually, it'll work out nicely enough anyway. So let's use the points, but let's use integer values. I think that students would tend to do that anyway. But in this case, you're going to see it didn't matter. So I'm going to sub in 3, 8 and 4, -28. And I'm going to create my system of equations that way. So I get 8 for the y value equals a 2 to the 2 times 3. Don't forget that x value is a 3, so 2 times 3 is 6, plus my q value. And then I'm going to have -28 equals a 2 to the, and in this case, the x value is 4. 2 times 4 is 8, plus q. So this ends up being 8 equals 2 to the power 6 is 64. So that ends up being 64a plus q. -28 equals 2 to the power 8. It's getting into awkwardly large numbers now. So what I always remember is 2 to the power 5 is 32. So 2 to the 6 is 1 more than that. So double it again, 64. Double it 2 more times, 128, 256. So this is 256a plus q. Call that equation 1. Call that equation 2. I'm going to take equation, let's see, I think it'll be easier if I take equation 1 and put it underneath here, plus q. And then I'm going to do a subtraction. -28 minus 8 is -36. 256 minus 64 is 192. So I get 192a, and then q minus q is 0. So a actually ends up being 36, -36 over 192. So a can be reduced, and 192 divided by 36, unfortunately, that doesn't work out super nicely. So that's going to be, let's see, I did it the other way around. 192 over 36 is 5 1/3, which is 16 over 3, which means this simplifies to negative 3 over 16 as my answer there. That's my A value. And then I can use that A value. I'm going to take this A value and I'm going to sub it into equation 1. That'll find my Q value. 8 equals 64 times negative 3 over 16 plus Q. 16 goes into 16 once, and 16 goes into 64 4 times. So this works out to be 8 equals 4 times negative 3 is negative 12 plus Q. Q equals 20. So now we have all of the components for our equation. Y equals negative 3 over 16. That's my A value. We had a base of 2 to the exponent 2x with a Q value of 20. And this is a perfectly good answer. I mean, if you can get this, that means you understand this whole procedure very well. But I can go one step further. If I want to express this in only vertical transformations, I can deal with that exponent 2 through a change of base. Or we could write this as y equals negative 3 over 16. And then instead of the 2 to the 2 to the x, I'm actually going to write that as 2 squared all to the x plus 20, which is negative 3 over 16. 2 squared is actually 4 to the x plus 20. And then that would be actually where I would end this. 3 over 16, 4 to the power x plus 20. And quite a bit going on there to come up with this solution. And there's not a lot on this from the textbook, so I've posted a worksheet to the web page, and I'll distribute that to the class as well to give you some extra practice on that. Especially those last couple of questions, those are representing some of the more difficult versions of this particular skill.